Alright guys, so welcome back. At this point we know that solving a trig equation starts off a lot like solving a regular equation. We need to isolate the variable term, only in a trig equation it's not just a variable term, it's a trig function. So once you've solved for that trig function, you then need to solve for the argument, the x or the theta. But the actual math to get there is just like solving a regular equation. So let's look at a fancier equation than we did the other day. Let's look at 2x squared minus x minus 1 equals 0. So a really good option, if this is factorable and if you're comfortable with factoring, is to factor this. And everyone has different ways of factoring. Everyone was taught something slightly different. So I'm going to kind of blast through my way real quick. And there I am. So I factored it. If none of that made sense to you, that is totally okay. You factor however you factor, and you're going to be just fine. So we set this little guy equal to 0. We set this little guy equal to 0. And we get x minus 1 equals 0. 2x plus 1 equals 0. We get x equals 1 and negative 1/2. So now where I think a lot of people might be interested in the factoring part that we just did, that's an Algebra 2 skill, and you can go back and brush up on that. What we're going to work on now is what if this wasn't just a variable equation? What if this was a trig equation? What if instead of x, that was a sine x? It would look like this. We would have a 2 sine squared x minus sine x minus 1 equals 0. And if we consider the sine x to be just like a variable, if we pretended that sine x was plain old regular x, or sometimes they like to change the variable. Sometimes they like to say, let's let u is a common variable that is used in substitution a lot. So we're going to substitute the variable u for sine x. So we have 2u squared minus u minus 1 equals 0. We can then factor just like we factored before. We get u minus 1 times 2u plus 1 equals 0. And then because u equals sine x, we can switch out u so that we have sine x minus 1. And we have 2 times sine x plus 1 equals 0. Now before we go any farther, you don't have to do this u substitution part. You don't have to do this whole section. If you're comfortable factoring with a trig function instead of a variable, you can jump straight from the first step here down to here, and that is totally fine. Either way you do it, if you use u substitution or if you jump from the beginning to the factored version because you're comfortable letting the trig function equate to a variable in your mind, either way, we get to here. So we've got sine x minus 1 equals 0, 2 sine x plus 1 equals 0. We've got our two little miniature equations here. And so solving this first guy, we get sine x equals positive 1. When does sine x equal positive 1? That's going to be a quadrantal problem, so I sketch it out. That happens at 90 degrees. I'm going to hold on to that for a second and jump over here. Go minus 1, divide by 2. You get sine x equals negative 1/2. And so now we have sine is opposite over hypotenuse. So we're going to sketch that out. When do I have an opposite of negative 1? That can happen here or here. And then a hypotenuse of 2 happens here or here. I've got little reference angles of 30 degrees. So when I look at these angles together, we have 210 degrees and we have 330 degrees. And again, looking at them together, we've got 90 degrees, we've got 210 degrees, and we have 330 degrees. They actually look somewhat evenly spaced out. So I'm going to check just to make sure. From 90 to 210, that is 120 degrees. from 210 to 330, that is 120 degrees. And then from 330 up to 90, that's 120 degrees again. So putting all three of these angles, this first guy and these second two guys, putting all three of these angles onto the same graph, we found that they're evenly spaced out all the way around the axis. And so we're going to pick the lowest number, the smallest answer. That's going to be our pi over 2. And we get x equals pi over 2 plus, we'd be spitting in 120 degree chunks. Now 120 degrees converted to radians, that's 2 60s. And 60 we know is pi over 3. If we switched out pi for 180, we'd have 180 divided by 3 is 60. So we have 2 60s. We've got 2 pi over 3. And we do that an infinite number of times. We do that n times. So our answer is x equals pi over 2 plus 2 pi over 3n. Now pausing this for just a second. If we started way back up at the beginning, if we were told to solve this equation, but then they gave us the very specific interval of on the interval 0 to 2 pi, when we got down here to the end, we wouldn't have to do this spinning around the circle thing or spinning in even chunks thing. We would just be looking for all the answers that occurred between 0 and 2 pi. And so if you look at one complete axis, you can see them all because the interval is 0 all the way around to 2 pi. You can see all the answers. And in that case, your answers would be pi over 2, and then 210 in radians would be 7 pi over 6. 330 in radians would be 11 pi over 6. If you're not good at converting from degrees to radians yet, or you need a refresher, it's not a bad idea to stop and practice for a little bit. Make sure you remember how to convert back and forth from degrees to radians. It'll help you out in the long run. Now, coming back to the beginning, I said, let's factor if it's factorable and if you're good at factoring. But what if it wasn't factorable? Or what if you just weren't really comfortable with your factoring skills? What could we have done with this quadratic right here? Well, we could always use the quadratic formula, in which case we would have, starting again, 2x squared minus x minus 1 equals 0. Using the quadratic formula, we would have x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So we've got 1 plus or minus rad 1 plus 8 over 4. We've got 1 plus or minus, this is going to be rad 9. Rad 9 is 3 over 4. 1 plus 3 over 4, that makes 4 over 4, which is 1. 1 minus 3 over 4, that makes negative 2 over 4, which is negative 1/2. We get to the end and we get the answers of x equals 1 and negative 1/2. That's not surprising at all. Those are the same answers that we got before. We were expecting that. It's the same problem. We're just solving it a different way. You can still use the quadratic formula on a trig equation problem, but this is where the u substitution is actually a pretty helpful skill. Let's start again with the same trig equation problem. So we've got 2 sine squared x minus sine x minus 1 equals 0. So if we let u equal sine x, now our normal quadratic formula is x equals negative b plus or minus the square root, blah, blah, blah. And we say x equals because x is typically the variable that is used in quadratic equations. X equals negative b, x is the variable that we're solving for. But if we let u equal sine x, what we would have is 2u squared minus u minus 1 equals 0. So now our quadratic formula is going to be u equals negative b plus or minus the square root of b squared minus 4ac all over 2a. The math plays out the same, and we end up with u equals 1 and negative 1/2. We simply did the quadratic formula using the letter u instead of the letter x. But now at the very end, we've solved for u. Now we come back to the u substitution idea of, hey, we're going to let the variable u equal sine x. So where we've got u equals 1 and negative 1/2, we're now going to say we have sine x equals 1 and negative 1/2. We're simply going to swap the u back out for the sine x. Then you can separate your equations. Sine x equals 1 and sine x equals negative 1/2. And this takes us right back up to where we were a few moments ago. Sine x equals 1 and sine x equals negative 1/2. So you can solve these quadratic trig equations by either factoring or using the quadratic formula and simply letting the trig function represent what would have been the variable. How about you guys try this one? See how it goes. Pause the video once I've got it written down and see what you can do with it. 2 secant squared x minus 3 secant x plus 1 equals 0. See what you can do. Pause the video. Come back when you're done. All right, I'm going to go ahead and factor this thing. So I've got 1, 2, I've got 1, 1. These are both going to be negative. My version of factoring, it works for me. I like it. If it makes no sense to you, that's totally okay. You can do your own thing. But when I factor, I end up with secant x minus 1 times 2 secant x minus 1 equals 0. I'm going to double check by foiling together real quick. Boop, boop, boop. Yep, I'm good. Okay, so I factored properly. Now I'm going to set this little guy equal to 0 and this little guy equal to 0. I get secant x minus 1 equals 0. I have 2 secant x minus 1 equals 0. So I'm going to add the 1. I get secant x equals 1. I'm going to solve for secant, but I'm going to switch to cosine. So I have 1 over cosine x equals 1. Multiply by cosine, I get cosine x equals 1. And the question is, when does cosine x equal 1? Looking at it, that happens here and here. So I've got answers of 0 and 2 pi so far. Let's take a look at this section over here. I'm going to add 1, divide by 2. I get secant x equals 1/2. Secant is cho-sha, that's hypotenuse, over adjacent. Can I have a triangle that has a hypotenuse of 1 with an adjacent of 2? No, that's not possible. So I'm going to disregard this whole side of the equation, but this side worked. And so this side still lives on. This side still solves the problem for us. So I look at my problem. I had 0. I had 2 pi. So I take the smallest answer, x equals 0, and I'm going to spin in full circles. That's going to be 2 pi n. And you can simplify 0 plus 2 pi n so that you just get x equals 2 pi n. All right, I hope that made sense, and I will see you again soon. Bye.